Welcome back. Welcome back to our live stream for the AnyLogic Conference. This is track one of the EMEA sessions. And welcome to those of you who are just joining us. Good morning. I'm pleased to introduce now Nicholas Fatras from the University of Southern Denmark, who will be talking on a multi-agent based simulation for a meat cooling facility's participation in the Nordic electricity market. Welcome, Nicholas.
Thank you, Gavin, and welcome everyone. So, as Gavin quickly mentioned, I'm Nicholas, PhD student at the Center for Energy Informatics at the University of Southern Denmark. And so what I'll be presenting today is a multi-agent-based simulation for a meat cooling facility's participation in the Nordic electricity market. Essentially, the idea is to model a large electricity consumer's participation in the electricity market and see how economically feasible, viable that is. Now, because I'm assuming that, I'll switch over, yeah. I'm assuming that, many of you won't actually be from an energy background or know much about the electricity market. So I'll give a bit of background on what demand response is, what flexibility is, what electricity markets are. And then I'll try to make it a bit more clear why I use AnyLogic in this context, because it might not be an evident use case, but hopefully you'll get some actually interesting ideas out of it with this kind of maybe different approach to agent-based modeling. And then I'll present what the overall kind of view of the model through this ecosystem visualization. And then we'll get into the fun bit with some experiment runs where you can have actually a feel for what the software looks like or the simulation looks like. So to give a bit of context, we're talking about an electricity system here. And it's important to remember, anytime we talk about an electricity system, it's essentially one big interconnected machine. And whenever you turn on the light switch, someone on the other side has to ramp up their production. And so essentially it's a constant game of supply and demand, which has to be in balance. And until now, this was so far so good. But with the increasing use of renewables, such as wind, which only blows when it blows, or sun, which only shines when it shines, you have less and less control over this supply side. So you need to get some new balancing mechanisms into the game. And you probably have heard of many solutions out there, such as batteries to store the energy and provide energy when you need it, or hydrogen, which was quite hyped recently over the past few months, or these super connected grids where you can shift electricity between countries. What I want to talk about today is something called demand response. And more than the technology, it's more a process management approach. So essentially, I'll use the analogy of this halftime at a football game, where particularly in England, for example, people would rush to the kettle to brew themselves a nice little cup of tea to watch the second half. The problem is that creates huge spikes, huge demand spikes on the grid. And if by mischance you happen to have not enough wind or sun on the grid at that point, then you might face some serious blackout issues, etc. So in that case, what you want to do is flatten the curve. And I'm using this term quite consciously because it's been used quite a lot over the past few months with Corona, etc. But instead of having your max capacity being dictated by the number of beds, hospital beds, this max capacity is dictated by the amount of power from your wind turbines or your solar plants, etc. So you want to shift this demand through time. And the way you can do that is, for example, pre-boil the water before the halftime, or turn off the fridge during halftime and turn it back on again afterwards. So having smart devices. Now you'll tell me this is all good, but I don't have these devices at home. So how do I actually implement this? And this is where the industrial consumer comes into play. And what we'll be looking at is this cooling process for a meat processing industry, where essentially you have the raw cuttings coming in at the top room, and then they're stored in this cooling room for quite a while before being processed further into sausage, canned meat, etc. And in this case, the flexibility comes from the fact that you have a minimum temperature and a maximum temperature threshold within which you can store your meat. And so essentially, if blue was your baseline electricity consumption, you can decide to turn off or turn on your refrigeration system depending on the grid's needs. And so you can provide this stabilization service. Now, again, interesting concept, but why would the industrial process actually be willing to do that? And this is where the market comes into play. You and I, as consumers, same as the cooling process, pay a certain electricity bill to a supplier with more often than not fixed prices. This kind of hides the reality which the supplier has to face, because the supplier needs to get his electricity from somewhere. And that's where the electricity markets come into play. Now, I won't go into detail about all the different sub-markets which constitute an electricity market. But what you need to understand is that each of these sub-markets has varying prices. So it's wholesale market prices. And the supplier, for example, is faced with this problem that typically in the morning when people wake up, or in the afternoon when they come back from work, prices are higher than during the night or at midday. And so what the supplier would like you to do, of course, is to consume at these cheap hours and avoid the peak hours. But because you have fixed prices, or because the industrial consumer has fixed prices, we're kind of very insensitive to these price variations. And so we're not really giving the grid or the supplier, we're not making them a favor here. So what we need to do here is to consume the industrial consumer, to convince the industrial consumer to consume at these low price hours. So this is essentially the aim of this whole simulation, to increase consumers' confidence in direct electricity market participation. And to do that, you need to, you need to address 3 points. You need to first show what options they have in the electricity market. You need to show the financial benefits of participating in the market or not. And then you need to make sure, of course, that the operational constraints are satisfied, like that the cooling temperature is satisfactory, that the meat doesn't go bad, etc. So that's why I call it a consumer-centric approach. We make sure that the consumer's requirements are met. And just to make sure we're all on the same page, what we're not modeling here, for example, a bunch of different industrial consumers and seeing how that would flatten out the curve. That's not what we're doing. What we're focusing on is one single industrial consumer. And so essentially seeing how different submarkets will affect both its operations and its revenue, depending on its operational preferences. Yep, so that's to create the framework. Now, what we're going to try to do in this simulation is go on a consumer journey. So essentially, starting with fixed prices, which is what the industrial consumer is facing at the beginning, we're going to start implementing what's called implicit demand response with variable prices throughout the day to try to reflect essentially these price variations in the electricity market. But again, it's only the supplier artificially varying the prices to try to reflect these market dynamics. Then we'll kind of incite the consumer to directly participate into the electricity market and see how much he can save doing that. And then finally, we'll have this combination of both having a contract with a supplier, but also being able to participate directly in the market. And so those are all different scenarios. And this is where the simulation becomes interesting, right? Because simulation is all about, it's a descriptive approach where you have a comparison between different scenarios, and you can see essentially what happens if I tweak this parameter or this parameter. So in that sense, I'll give it some AnyLogic kudos. Another kudos is maybe if you look at the top, some of you might have noticed this timeline, because essentially each of these markets has a certain bidding deadline. And so the timing at which you receive your information, for example, your forecast for your demand or forecast for wind and solar production, will be very important in terms of for your market strategy, at which price and which volume you're willing to bid in each of these markets. So this calls for discrete event simulations, right? So where timing is quite important. So again, that's why AnyLogic was quite interesting in that regards. And finally, if you look at this kind of diagram I quickly drew, you have these different agents, right? You have the consumer in contact with the supplier, in contact with these different electricity markets, which are all modeled as agents. And so you have this agent interaction, which will influence how much information each agent has, and therefore what market strategy they apply. Right, so I think this kind of sums up what I said at the last slide. Essentially, AnyLogic is very, very attractive in this case because it allows simulation with by tweaking parameters and having a scenario comparison approach. It allows to have discrete event simulations because timing is crucial for market strategy. And well, it's an agent-based modeling tool, so it allows to accurately represent agent interactions and accurately model market strategies. So I'm now going to dive into one small technical implementation, which I think is interesting and could also be of interest of anyone not necessarily in the energy field. But what we kind of tried to do in our center in general, a method we're implementing, is this distinction between roles and agents. So essentially, in an electricity system, you have a bunch of different base roles, which pretty much always have to be fulfilled. For example, role 2 could be bidding into the electricity market. But depending on the business model or the market context, this role will be implemented by different agents, right? So for example, at the beginning, you could expect the supplier to be bidding for you in the market. So this role will be applied to the agent. While in a future business model, agent 2 being the industrial consumer will bid himself directly into the market. And so instead of having to redefine the agents every time, you can just essentially just reassign which roles the agent implements. And so these roles are these interfaces in AnyLogic, which essentially inherits from the Java concept of interfaces. So these are kind of blueprints which you assign to the agent, and based on the blueprint the agent is assigned, he needs to fulfill these specific roles. Now, what does this imply on the ecosystem level? I've shown essentially that the only two differences between these maps is the assignment of this role. The flexibility manager here is assigned to the industrial consumer, while in this case it's assigned to a separate agent called the aggregator. And if you look at the roles, the communication is still the same, so you won't have to change anything in this case. The only thing is the agents which these roles are assigned to are different, so you'll have different agent interactions, so different access to different information, and therefore different market behavior. But for you as a simulator, it's not that much extra effort. You just need to assign the right roles at the beginning of the simulation. Now, I'll focus for the actual runs. I'll focus on this context because it's the one most relevant for the Danish context. But now let's maybe dive into what the simulation actually looks like when you're an industrial consumer wanting to know how much you would make in the electricity market. So what you would start with is essentially choosing a market strategy, right? Whether you want to be flexible or not, and then whether you want to have these. So these are all kind of different terms showing essentially how at which step in the consumer journey you want to be at, whether you want to bid yourself or whether the supplier does it for you. And the user interface is supposed to guide you by graying out the areas which are not appropriate for a specific step. So for example, here, retail markets should not be available as an option when you bid explicitly. Now, this is all for the market on the market side. On the consumer side, you need to, of course, you need to say how much flexibility you're willing to provide in the market, right? So in this specific industrial process, what we're interested in is what is the minimum temperature that's allowed and what is the maximum temperature that's allowed. So in this case, we're varying between 0.5 and 5 degrees. If you vary by more, then you might have more flexibility and you could bid more volumes on the market and maybe make more savings. And then you can also tweak other parameters such as the time shift is the duration which you allow before the temperature has to go back to normal, or the amount of hours you're willing to shift from your baseload consumption. And I won't go into the financial risk willingness, but that's essentially more financial-based strategies. Yes, so that's essentially the parameters which the user inputs before launching the simulation. And then once you have done that, I'll go over 3 different sets of experiments I've done just to illustrate how this can be used by the consumer. So I'll go over a simple simulation experiment first, just showing the current potential. Then I'll do a CompareRuns experiment to evaluate different market options, and then finally a parameter variation to do a sensitivity study on one of the parameters. And so if we launch the simulation, I'll choose an explicit demand response, which means directly participating into the market itself without this middleman, without the supplier. So that's this business model we're considering. Once you start the simulation, you get these. Well, this is the results the consumer is interested in. On the left side, you have the financial impact of demand response, right? So you want to know how much you're saving or not. And essentially, as long as the green line with flexibility is above the blue line, it's happy days. It means you're saving essentially on your bill. These are more, I would say, long-term parameters, essentially measuring how well your process is correlated with the market prices, not something that is maybe relevant for this particular simulation. But on the left side, what you see here is the more physical approach, so the operation, how it impacts your operations. So this is just to make sure that overall you supply the same amount of energy, right? That you don't disturb your process. This diagram on the lower left shows whenever you have a deviation in temperature, in which direction does it usually go into? So for example, over those 24 hours, in the morning, you see that usually they tend to decrease temperature, so increase power consumption because power prices are low at that point. While in the morning, the temperature tends to increase because power prices are high, so you want to shut off your cooling process. So that kind of tells you, okay, yeah, the simulation seems to behave well. It makes sense with what I would expect. And then at the bottom, you can follow, of course, your power consumption initially, and then based on the plan load, and then the flexible load. And then, yeah, so that's the overview for the industrial consumer. That's the ecosystem overview of the different agents involved within the simulation to actually do this bidding process. That's the parameters you input initially. And then finally, you can also check like the results for the different agents making up your ecosystem. For the industrial consumer, this is just to make sure essentially that the supplier behaves as accepted in the contract, right? So that his income stays around zero, which is what you would expect for a supplier without profits. So, but I would say for the industrial consumer, the main results of interest are these here. Right, so this is for one simulation. Now, what we want to do is compare different scenarios, right? This is the power of simulation in general. So what I'm going to do is first run a basic simulation with constant rates, so no demand response, no flexibility, and with fixed pricing, so same prices for every hour. And this essentially is how your bill evolves with time, right? I mean, negative prices means you pay, you don't receive money. Then the same, but with a day ahead pricing, you see that you actually are improving on your bill. You pay less. Then we saw, this is going a bit fast here maybe, but essentially the result from the implicit demand response was to give you 1% saving, which isn't, I mean, huge, but I think for industrial consumers it can already make a difference. And I think it's important to remember here that it also depends on the market prices, right? Like if the market prices are not variable enough, then you might be as flexible as you want. Your savings won't be that great. But here, the interesting thing to see is that when you combine different markets, yeah, so the difference here is not great, as I said, because of market prices. But what's interesting to see is essentially different market combinations can give you different savings. And then the last thing I wanted to show, yeah, a bit of time left, is this parameter variation, right? Because what you're interested in is if I change my maximum temperature, if I increase that, I can bid more on the electricity market and therefore make more savings. So what we'll do here is on this axis, the max temperature is going to vary between 3 and 8 degrees. And we'll see for each of these values how first of all, on this axis, how your overall electricity bill looks like. And this one will show essentially the distribution. So I'm modeling over 3 months. And so for each days within the month, I'll see how much I save compared to my base load. And so this just uses a 2D histogram plot to show the frequency distribution of savings for each of the days. And so you'll see here as the parallel runs, they're running with, you don't have to wait for one simulation to be done to start with the next one, which is quite a nice feature of AnyLogic. And there, here we see the results coming in one after the other. The table's getting populated. And what we observe as an interesting result, for example, is that increasing your max temperature by ½ degree will give you a certain amount of savings. But then the more you increase, the less and less marginal benefits you get out of it. So there's kind of a saturation effect. So I could tell the consumer, the industrial consumer, yeah, maybe increasing my max temperature by another ½ degree isn't actually worth it based on the savings that I can make out of it. So that's an example for the max temperature, but you could repeat that for different parameters, right? What's the maximum time I allow to deviate by, etc. So that's a sensitivity test, which is allowed by AnyLogic's neat parameter variation experiment. And so to wrap it up, I think what I want you to remember is that the whole point is to encourage industrial consumers to participate in electricity markets. And to do that, we need a descriptive approach. So we need to let the consumer decide himself what parameters are acceptable to participate in the electricity market. And then we'll try to, it's important also to remember that we have this consumer-centric approach. So we're focusing on the results for the industrial consumer, not for the grid operator, but we still need to model the logic of all the other market players. And finally, we have a modular approach because we need to test different business models. So we need to be able to shift the roles and distribute them to different agents. And the conclusion is that you can get revenues that vary a lot depending on the adopted market strategy and the operation willingness. And that's why having this comparative approach through simulations is very relevant. I'm just going to finish up on this final slide. Essentially, the larger aim of my thesis in general is to apply the simulation to a bunch of different industrial consumers in two different contexts, the Danish and the Chinese context, because it's a Sino-Danish partnership. And there you can really see the usefulness of this modular approach, because the two markets being quite different in structure, for example, a role assigned to a market actor in the Danish context will be applied to a regulated actor in the Chinese context. And in that case, you can just quickly switch the interfaces from one agent to the other, and then implement it to a bunch of different industrial processes, which could have some demand response. That was it for me. So thank you for your attention. I hope you got something out of it. And if you have any questions, yeah, feel free. Or otherwise, you can always write me to my email. That was it.
Thank you, Nicholas. Yes, so we have a question here. Did you also take into account that overcooling in the early morning and when it's cooler outside has a cooling efficiently benefit?
Yeah, so when it's cooler outside than inside, of course, I turn off the cooling process. And so that's why in Denmark particularly, this whole cooling would only be running from typically May to September. And the overcooling itself is not something I've looked into, but essentially the whole idea is to have the modeling of the industrial process itself is implemented in very separated functions. So someone who is maybe an expert in cooling processes can focus on this specific function in this specific agent, and that essentially allows to separate. I've tried to separate the different components so that some specialist in cooling can work on this specific agent without affecting all the other agents in the system. So I would say I've used a pretty simple, straightforward cooling process to model it, but of course it can be improved later on. Yeah.
So that's kind of modularizing the.
Yeah, exactly. I think the whole idea here is to really make it modular, because what I've done for the cooling process, I've also done for a greenhouse, and so what you want to do is just switch the industrial process without having to switch all the other agents in your model.
Right.
No.
Cool. And I just have a question coming through here at the end. Is there a white paper to read that maybe could be linked to?
Yeah. Well, I mean, there's a paper in the making, and
Okay.
I've done a publication based on a rough version of this model, so I can share the publications. How would you do that actually through this platform?
Yeah, if you hopefully return into the conference platform, and people will be able to contact you directly by messaging, and also there'll be discussions and roundtables there.
Sounds good.
So yeah, so absolutely encourage anyone watching who wants to get in touch with a specific question like that, then reach out to Nicholas through the conference platform. There's a couple of questions coming in right at the end here, and I think we've got a couple of minutes. So asking, can you talk a bit more deeply on how these roles were defined and how you use the interfaces?
Yeah,
because it seems like an interesting implementation.
Yeah. So essentially, for each of these interfaces, maybe I can. Oh, it's quite far back, but yeah. So for each of these interfaces, I have. Actually, I think I have a slide at the end. Yeah, that one. So essentially, each of these roles will have communication functions, which are these blue functions at the top, where you essentially have these get functions and send functions, where you get and send data. And that's the public functions that are visible to other agents that want, or other roles that communicate with that role. And then you have these internal functions, those are private, and those define the logic. Those are kind of the meat of the role. But what you define initially in the role is this blueprint, right? So you just say it needs to have this as an input, it needs to have that as an output, and it needs to implement this function. But then the logic of the function itself is only implemented once you actually implement it in the Danish context or implement it for this specific business model. And then the interface, the communication between interfaces is essentially you have these interface types, and so you send a message to this specific interface. So the agent, when you initialize your agent, you say this agent will implement these specific interfaces, which means it implements these specific roles, and then you can essentially track the path to that specific agent initially when you initialize for the communication. But once you've assigned the right agent for the communication initially, then the roles just communicate with each other. So yeah, the roles itself are just a blueprint, and then once you initialize your model, you need to assign the role to a specific agent.
That's great. Oh, thank you for that. I hope that answers the question. There's one here on validation. They're just saying, did you do the validation of the model with users? And so to what extent were the users of your models find your model interactive, informative, and engaging, etc.?
Yeah. So all the data I've used for the cooling process is from a industrial partner we were working with. And then the electricity market data is just live open source data, which is made available in Denmark. So it's all based on real data, and we made a report for the specific industrial consumer we had to work for this cooling process. And as I mentioned, the feedback we got is unfortunately the price differences at that time weren't high enough, essentially, to create an incentive to implement that. Mm-hmm. But I don't know if some of you have been following, but this year the prices have gone through the roof in many markets across the world. So it would be very interesting to actually redo this for updated market prices. And in the future, market prices are expected to vary more and more. So there's going to be more and more incentive to be flexible and shift your processes. So yeah.
That's great. Yeah, it's just something that's hitting the headlines at the moment. Quick last question. Which market showed most potential for this process? The day ahead, the intraday, or the imbalance?
So it depends on, the answer is it depends. It depends on the industrial process you're looking at. But for a cooling process, what's interesting is that you have continuous operation. And so essentially that means that you can have small changes in consumption without it affecting your process too much, compared to, for example, a batch process, where if you stop it for 30 seconds, then that ruins your batch for the whole hour. A cooling process has this thermal inertia, which means that you can stop for a few seconds and it will still more or less keep the same temperature. And so essentially that means that these small, let's say, short reaction time markets, where you just provide a bit of power for a small duration, work quite well. So in this case, it would be the regulating market, the intraday market, etc. Yeah, but that's more domain-specific question, I guess. So I'm hoping the one who asked the question kind of knows a bit about electricity markets. Yeah.
Cool. Thank you very much. There's just one last question coming through about asking if it's possible to get the presentation from Charles here. I think that's probably a question that can be best answered on the platform through messaging. So I encourage you to reach out there. Well, thank you for that, Nicholas.
Thank you.
Have a great day, and look forward to seeing you around on the platform, and take care.
Yeah, thanks for hosting, and thank you for listening, everyone. Have a good day.
Okay. now we've got coming up a workshop. So if people would like to stay online, in a few short minutes, we'll be starting a workshop with Benjamin Schumann.